This video is going to talk about the RAM rule for estimating sums. Now, before we get into that, I do want to talk a little bit about calculus in general. We're kind of at a crossroads of such in calculus. If you think of these kind of towers of calculus, we kind of have our foundation of everything that is based on. And everything in calculus is based on limits. That's where we started in limits back in chapter 2. And everything we do in calculus is based on limits. And as you think back to then, the first half of what we've done has been derivatives, right? We found derivatives. That was chapter 3, was how to find derivatives, chain rule and product rule and quotient rule. And then chapter 4 was using derivatives to find maximins and concavity and optimization and all that kind of stuff. The second half of this class, we're going to be talking about, this is differential calculus that we started with. The second half of calculus is going to be known as integral calculus, and we're going to be talking about finding integrals. Now, both of these are completely based on limits. Now, just like with derivatives, once we get into some of the everyday kind of stuff, we may not think about limits as much, but limits are the basis for everything we do in calculus. And then eventually, we will get to this bridge that connects everything together, that kind of connects our two towers, and this is known as the fundamental theorem of calculus. So that's kind of what we've been, right? This was chapter 2. This was chapters 3 and 4. We are now starting chapters 5, and then we will look at some of 6 and some of 7. These last couple, we will hit just a little of this and a little of that. So let's go back to our sums. So we're going to use the RAM rule today, and the RAM rule is called the rectangular approximation method. That's what RAM stands for. Now, to get us going, I want to go back to something we looked at the very beginning of the year, right? We looked at this problem at the very beginning of the year, and we said if you graph 2x on 0 to 2, that would be, if I can draw a straight line, that would be this line. And we wanted to find the area under the curve. So we would come down here and we said, what's the area of this rectangle? Or excuse me, this triangle. It's 2 by 4. So our area is 1/2 2 times 4. So our area is 4. Now, I'll just mention here, you can also think of this, if you were looking at the area here, you see we can have 1, 2 squares for area. If you think of this and those added together, that would give me 3. This and this would give me 4. So one way we could approximate that would be by looking at the number of blocks. But to find the exact value, we use our triangle formula. Now, the second one we looked at was x squared on 0 to 2, and x squared was harder because x squared was this curved quadratic that went like that. And we couldn't just use an area formula because of that curved shape. Now, we can kind of see the number of squares in there, but that's hard to figure out exactly. It doesn't fit quite as nice. Now, we know that that is smaller than if we drew the triangle. So we could say, well, we know it's got to be less than 4. But to find that area under the curve, we need to use more. We need to use some calculus. And that's why we looked at this at the beginning of the year where we said we couldn't figure that out. So that's what we want to kind of lead into. So to get us started, let's look at a situation. A train moves along at a steady rate of 75 miles an hour from 7 to 9. So drove for 2 hours at 75 miles an hour. What's the total distance? And I think most of you, just kind of in your head, you can do that. You can think about that. And you would say, well, that would be 150. But I want you to think of this as a in a different way. Imagine for a second that we did this. Imagine that we graphed that velocity. We said this 75 miles an hour was our velocity function, and we graphed that velocity function of 75. It's a constant function, but that's fine. So it's just this horizontal line. And then we wanted to find the distance traveled between 7 to 9. So this yellow area would be our total distance traveled. So the area of this rectangle was our 150. Now, I don't think anybody thinks of it this way. I doubt any of you thought about it that way, but that works. Now, why would we want to take this relatively simple problem and change it to that harder problem? Well, what happens if our velocity was not steady? What happens if our train was not traveling at a steady rate of 75 miles an hour? Let's say this was the rate that our train was traveling. This is still a graph of the velocity, right? We're going up hills and down hills and around curves and slowing down and speeding up. So our velocity is varying. Our rate of change is changing. But if we have that, if there's still a way for us to find this area underneath the curve, that area is still the total distance. Actually, excuse me, this is displacement, not distance, but the same idea. This is always positive, so we're okay here. We're always moving in one direction. But you get the idea. We can find the total distance traveled by finding the area under the curve. And the way we want to find that today is by using approximation. Here's an example where our total distance and displacement would be different. If we would look at this graph, you would have this area above, this area below. You'd have to subtract the area below because this would be negative, this would be positive. So if we looked at this, if we found this, this would be, this rectangle here is 2 by 3, so that's 6. This is 2 by 3 of 6, this is 3. This is 3. So this area up here is a total of 12. This area down here is 2 by 1. This is negative 1. So our displacement would be 11 because you subtract them. Our total distance traveled would be 13, right? Because this top part says you went 12 this way and then back 1. So a displacement of 11. But your total distance traveled is 13. So that's kind of what we're finding. We have to find this area. In this case, it's nice triangles and rectangles. We can just use our formula. But what if it's not triangles and rectangles? What if it's something like this? Estimate the area bounded by 9x squared, the x-axis and y-axis. So we're looking at this area under here, underneath the curve, okay? So we can do this with rectangles. So I just wanted to kind of explain this, how we could do this. One, we could do this with rectangles of width 1. So if I would draw these triangles, this is rectangles. This is width 1. And there would be a rectangle. Here's another rectangle. Goes up to 2. And then my last one would be 3. So there's 3 triangles that have width 1. Now, it also could ask, What about width of 0.6? So 0.6, there's to be here, go over and up, and then 0.2, I'm doing this really rough, 0.2, 4, 8, and I think you get the idea here though. So as we do this, we get more and more rectangles. And so as our rectangles get smaller, we end up with maybe a better approximation. We get a better answer. Okay, so that's kind of a general idea of what we're looking at. So let's look at some examples now, kind of get the nuts and bolts of this. So we have x squared on 0 to 2, and we're doing x squared because we can kind of easily do the math with that. We want to draw rectangles of width 2. Another way of thinking triangles, of width a half is our total number of triangles, and sometimes we'll talk about our rectangles, is 4. So on these two, we have 0 to 2. So 0 to 2. And if we're going to do our n is 4, or each rectangle is a half, if we draw those, then we're going to have 1.5. And this is 1.5, which I will just say is 3 halves. So here is a half, here's 3 halves. Now, for both of these, we're going to have some different rectangles. I keep saying triangles, I'm sorry. First off, we're going to have a left-hand rectangle, which means if we go, let's look from 1 to 1.5, between this rectangle's base here, we are using the left-hand side, which is 1, so we are going to go up till we hit the graph, and then go across to make our rectangle. Over here, we have a right-hand rectangle. So same interval, we're going to go up the right side and then make our rectangle. Now you can see this may make the rectangle go below and be a little under what it should be for our approximation. This one may be above, which is a little bit over, but it kind of depends on your graph. If your graph was going down, a right hand would be under. So it kind of depends the shape of your graph also. So we want to do this for each of our rectangles, our 4 rectangles. So we go to the left side and over. We go to the left side and over here our left side is just flat. Over here we go to the right side and over. We go to the right side and over. And we go to the right side and over. And you can see, because this is increasing, our left-hand approximation will be under the true area, and our right hand will be over the true area. Now, the next thing we want to do is we want to find what the area is. So over here, let's find our area. Now, for this first rectangle, the width is 1/2, and the height of our rectangle is 0. That's not really a rectangle, but we get it. The next one, our width is 1/2, and the height, this is the left-hand, switch colors here, the left-hand side. And remember this, our function here is just y equals x squared. So the functional value there, the height of this rectangle is 1/4. The next one is 1/2 times 1 squared, which is 1. And the last one is 1/2 times 1.5, or 3 halves, which is 9/4. And if we evaluate all of those, we get 1.75. Now, let's do the right hand. The right hand, now you'll notice every single one of these 4 rectangles are all 1/2. So I'm just going to pull out the 1/2, make our calculations a little bit easier. And then I'm going to take the right side. 1/2 squared is 1/4. 1 squared is 1. 3/2 squared is 9/4. And the last one is 2 squared, which is 4. If I do that, I get 3.75. Okay. So those are our two ways we can draw our rectangles. And we get a different answer. This 1.75 is a little low, 3.75 is a little high. But what we've done is we have found a rectangular approximation method, the RAM rule, as I call it. And we have 3 types. We just did the left hand. We just did the right hand. We also, maybe a little bit better approximation, but a little bit more work, is we could do the midpoint. So let me just kind of show you what that means. If we did the midpoint, we have our 0, 1, 2, 3/2, 1.5, and we have our rectangles. But for this rectangle, if we're looking at the rectangle between 1 and 3/2, we go to the middle, we go up, and then we draw that rectangle. We go to the middle, and we draw that rectangle. We go to the middle, and you see this can be good because we have some parts over, some parts under. Kind of depends on the shape of your graph. Okay. Now this is a little bit harder because you have to find these points here. This is 1.75, and this is 1.25, and this is 0.75, and this is 0.25. So you got to find those, and now you got to square those values and do all of that. Okay. So we understand this is 4, n is 4. Now, if we would want a better approximation, one of the things we could do is increase our number of rectangles. So instead of doing this with 4 rectangles that we did before, we could do this with 8 rectangles. And let's say we do the right one here. So my line's not very straight. So we go over and down, over and down. So we have a lot more rectangles here. And the more rectangles would give us a better approximation. Now, that's also a lot more work. So we're going to look at this 2 different ways. One, we do want to understand how to do these by hand for a small number of rectangles, like 4 here. We want to be able to draw the picture between the left hand and the right hand to understand the difference. But we are, to kind of help us do this, help us to do these calculations, we are going to use kind of a computer or a calculator. Now, I have here to say to use this on a calculator. I'm not going to, it deals with downloading software on your calculators. We're not going to do that. But I do have this website. Now, instead of you going to this website, what I have done is this website is on Google Classroom. And it's an integral approximation calculator here. You can just click that, and then that will take us to this calculator. Now, if you look at the problem we were just looking at, our function was y equals x squared, and we were on 0 to 2. Now, for this website, this is going to be called our A, this is called our B, and we had 4 rectangles. So let's look at it. So our A is 0 to 2 with 4 rectangles. And if I pick the left, here is our 1.75. And you can see that graph right there matches our left hand rectangle. Now, if we wanted to find right, or let the computer do the work, we click right, and we get 3.75. Or we could click midpoint and you get those right there. Okay. Now, this does have something on it called trapezoid and Simpson rule. These are something you don't get to. They're a little bit more complicated. You get to those in Calc 2. We are going to look at the midpoint, the right, and the left. Now, if we wanted a better approximation, we said we could go to 8 rectangles. And now our approximation is better. There's the left, there's the right, there's the midpoint. If you wanted more, let's say we wanted 20 rectangles. There's the left, there's the right, there's the midpoint, and you can, looking at the answer here, you can see we're starting to get to a much smaller approximation. So if we just keep raising this value, there's the midpoint, there's the right, there's the left. There is a limit on this end. I think it's 100, maybe 200. There's the left, there's the right, there's the midpoint. You're seeing we can get closer and closer. Let's see if we can go up to 200 here. If we go to 200, our midpoint's 2.666. My right is 2.68, and my left is 2.64. So you can see we are in that 2.6 range. So on your homework and on some of these, like I said, we want to understand how to do this by hand, but we also can do this on the calculator to kind of understand what we're getting, okay? So let's look at this example. Negative 2x squared plus 4x plus 8 on 0 to 3, okay? And we need a value of n, so I'm going to start with 10. So I'm going to go to this website. I'm going to type in this. This is negative 2 times x squared plus 4 times x plus 8. Our n is 10. We are on 0 to 3. There is my left. Now I don't want 110. I want 10. If I can zoom out a little bit, you got to do this a couple times. There is my approximation. And then my right is that, and my midpoint is that. So if we went back here, we could write this down. This was 24.81. This was 23.01. This is 24.045. Now, if we want to get a better approximation, we can go to 50. And now our midpoint is 24.2. Our right is 23. Oh, I put 15, I'm sorry. $50. My right is 24.0018, my midpoint. My right is 23.8164, and my left, and then we can fill those out over here. I know your homework has you do something like this where it tells you what n to use and has you fill out a chart like this. And then it asks you to go to 100 and so forth. And to do that, use this website that's on Google Classroom. And then once you go higher, the eventual goal is, well, can we guess what the value is? It's like what the true actual value is. There's the left, there's the right, there's the midpoint. So if I'm looking at this and I said, man, what would I approximate that the true value be here? I'm thinking it looks like about 24, right? And as you can just make n go higher and higher and higher and higher, eventually your left, right, midpoint will almost be the same value. Like I said, I don't think this software is higher than 200, but we can theoretically go much, much higher. Now, where we're actually going with this is what happens if we would do all this and we would look at the limit as n goes to infinity. What happens if our number of rectangles goes to infinity to our answers? That would give us exact value. That's where we're headed, but that's for another day. Now, the last thing we can do, these are some of your homework here. Approximate the area of the curve given the interval using 4 left-hand rectangles. You can see they have drawn the rectangles. And so you can see here you can determine what the width is. You can determine what the height is by just putting -5 into the function. Also, you can check your answer by using the software on the computer. Obviously, you need to understand how to do this kind of by hand using your calculator, obviously, to give you this approximation. But if you want to check it using that website, that is okay. Now, what happens if they don't give us a function? Let's say they just give us data. A rectangular swimming pool is 30 feet wide, 50 feet long, and the table below shows the depth of the water at 5 feet intervals from one another. Estimate the volume using right hand or midpoint values. So what you have here is your intervals would be, there is 1 interval, there is 2 intervals, there is 3 intervals, there is 4 intervals, there is 5, there is 6, there is 7, there is 8, there is 9, there is 10. And now if we are using right hand, we would use the right side of each of these. If we were using left hand, we'd use the left hand side. Midpoint's a little bit harder to do, and I'll explain that in a second because we don't have that value. So if I wanted to try to find my area, my first interval here is from 6 to 8.2, okay? So this is my x, my width is 5, from 0 to 5, and my right value is 8.2. Plus my next subinterval from 5 to 10, that's also 5. The right hand is 9.1. Plus 10 to 15 is 5, and the right hand interval is 9.2. And so forth. And then you could just continue all the way down, and you would see my last one, 45 to 50, is 5, and the right hand is 13, and I'm able to evaluate it from there. Now you'll notice if I went left hand, it basically is the same, just this last value is different. If I go back to here, you will notice we have 1/4, 1, 9/4. 1/4, 1, 9/4, that you're kind of doing the same for all of those. It's just when your right hand interval, you're using this last value, you're not using the first, and when you're a left hand value, you're using the first one. So a lot of the same numbers, whether you're using right or left hand. Now, if we were going to try to do this just with the midpoint, this is a lot harder because you can't say, well, 2.5 would be, you don't know that. So if we wanted to use midpoint, we would only be able to use 1 interval, 2 intervals, 3 intervals, 4 intervals, 5 intervals. We have a lot less. And then we'd have to use these values as our midpoint values to try to figure out what our total is. All right, that is our RAM rule, our right-hand approximation method. You are now able to do the homework.